Okay, so we're going to record this once and for all here. So we are looking first in the photoreceptor. Remember, the photoreceptor, when the light is off, has one response. And then when the light is on, we'll flip everything and we'll get a different response. So when the light is off, there are no photons. The photons normally activate this, but since there are no photons, this G protein coupled receptor, which is rhodopsin, is not able to activate its G protein, which is transducin, which is then not able to go activate phosphodiesterase. So phosphodiesterase is not working. And so the cyclic GMP is available to open the cyclic GMP gated channels and allow sodium in. Allowing sodium in depolarizes the cell, and that depolarization leads to an increase in glutamate release. So when the light is off, cyclic GMP gated channels are open, sodium comes in, depolarizes the cell, and we get an increase in glutamate release because of the depolarization. Now in the photoreceptor, right, there's one response when the light is off, and that's the opposite of what I think it should be, but it's an increase in glutamate release. And that glutamate is going to do two different things depending on what bipolar cell it binds to. If it's bound to, or if it's connected to an off bipolar cell, then that's going to lead that off bipolar cell to increase glutamate. And it does it by binding to AMPA receptors, again, on those off bipolar cells. Sorry. So when you have your glutamate, it binds to the AMPA receptors. Those AMPA receptors open, and you get an increase in sodium that depolarizes that off bipolar cell. So when the light is off and there is glutamate release from the photoreceptor, the off bipolar cell releases glutamate. And then that leads to the off retinal ganglion cell to have an action potential. That's the easy part. Okay. So that glutamate, same glutamate, if it's binding to the receptors on an on bipolar cell, these metabotropic glutamate receptors are, again, the opposite of what you would expect with glutamate, but these are inhibitory. So what they are able to do is activate a different G protein, which is then able to go and open potassium channels. Potassium's more concentrated inside, so that's going to leave the cell, making the cell more negative, which is a hyperpolarization, and lead to decreased glutamate release. So in that on retinal ganglion cell, there's no action potential. Now, if we switch it and we turn our light on, then we have a photon of light is going to bind rhodopsin. That is going to activate transducin. The activated transducin G protein is going to go and activate phosphodiesterase. The job of phosphodiesterase is to break this down from cyclic GMP into GMP. And then that is going to close these cyclic GMP gated sodium channels and lead to a decrease in sodium. So then that decrease in sodium is going to hyperpolarize and we don't get glutamate release. So when the light is on, this signal transduction cascade is active, closes those cyclic GMP gated channels, hyperpolarizes the cell, and when the light is on, no glutamate gets released. So in the off bipolar cell, no glutamate means these are closed, means there's no sodium, means this off bipolar cell hyperpolarizes, and then there is a decrease in glutamate release. So then that means there is no action potential in our off retinal ganglion cell. And because we have less glutamate, that means these are going to be off and not active, which means the G protein is not going to be active, which means it cannot open these potassium channels, which means we have less positive going out, which means we depolarize the cell, which means we get an increase in glutamate release. So when the light is on, no glutamate release from the photoreceptor. But because we don't have the glutamate, we're releasing the inhibition here so that then we can get glutamate release in the on bipolar cell, which means that in the end, the on retinal ganglion cell is going to have the action potential. So if we look at that in this model, right, when the light is off, the cyclic GMP opens the cyclic GMP gated sodium channel to increase sodium, depolarize the cell, and lead to glutamate release. And so remember, in the light off, both of these photoreceptors have the same response because they're responding in the same way. The only difference comes in what type of receptors they're binding at the postsynaptic membrane on either the off bipolar cell or the on bipolar cell. And so in the off, when the light is off, there's that increased glutamate release, and that's going to cause the off bipolar cell to release glutamate. And that is because AMPA receptors are on the off bipolar cell. So when glutamate's there, the AMPA receptors open, you get increased sodium through the AMPA receptor that depolarizes the cell, and that leads to an increase in glutamate release from that off bipolar cell. And then because this retinal ganglion cell has specific receptors here, that's going to lead to an action potential in this off retinal ganglion cell. Now, when the light is off, again, same response here, but because there are different glutamate receptors, here they are inhibitory metabotropic glutamate receptors. That's going to activate a G protein that opens a potassium channel, which causes potassium to leave the cell, which hyperpolarizes the cell and gets no glutamate release, and then no action potential. And if we look at that when the light is on, that photon of light activates rhodopsin, which is our G protein coupled receptor. That activates transducin, which is the G protein. And then that G protein, that transducin, is going to activate phosphodiesterase, which is the enzyme. That phosphodiesterase breaks down cyclic GMP to GMP. So now you don't have as much cyclic GMP available. So that cyclic GMP gated sodium channel is going to close. On that less sodium in, that's going to hyperpolarize the cell, and you're not going to get any glutamate release. Now, the off bipolar cell needs glutamate in order to depolarize because it has those AMPA receptors. So when there's no glutamate, those AMPA receptors are going to close. So no sodium is going to come in, and that's going to, oh, hold on. I even make mistakes. So that's going to hyperpolarize the cell, and you're not going to get any glutamate here. Because there's no glutamate here, AMPA receptors are excitatory when glutamate binds them. And if you don't have the binding, then you're not going to get glutamate release. That means no action potential from this off by retinal ganglion cell. Okay, so again, same response in the photoreceptor, because when the light's on, the photoreceptors do the same thing. The only difference is because you have a different receptor here. So, or a different glutamate receptor, right? So you have the metabotropic glutamate receptors, which are normally inhibitory, but those are not going to be active. So those potassium channels are going to close. So the potassium, that positive, is going to stay inside the cell, and that's going to depolarize the cell. And so when the light is on, the on bipolar cells are going to release glutamate. And then that's going to give an action potential in this on retinal ganglion cell. So I know some of you learn better by words. So I hope this is a different way to see it and a different way to process it. And again, seeing it in multiple ways is what's going to help you. So my recommendation is to review this again. Start with a blank one, not an upside down one, just a blank one. And try to represent that in any way that works for you. So some of you may, on this one, so you have light, and then that's going to activate rhodopsin, et cetera, et cetera. So try with that blank one, see how much of it you get correct. And then after you've seen what you don't get, review it again, and then go to another blank one and try it again. It's all about repetition. You can get it. It just takes some time.